So these questions you've got, this is like a little drill starter activity. So number one, differentiate that. Hopefully you can almost do that by sight now. Refer to your table if you need to, but that's hopefully fairly straightforward by now. Remember the notation for the differential. And then number two, what does that differential that you've just found tell us about the original function? Number three, look at that sketch there that you've got. That's a sketch of velocity against time. So velocity on the y-axis, time on the x-axis, and a plot is giving us a straight line. There it is. So number three is, what does the gradient of that line tell us about the object that's being described there? So this is a velocity time graph for an object. What does the gradient of that line tell us in terms of the motion of that object? And number four, thinking about what we plotted, velocity against time, what does the area underneath this curve tell us about that motion? And then we want another graph of, this time, force against extension. So very like the assignment you're asked to do in the science and mechanics, plotting force against extension for a wire that's being stretched. Again, number five, what does the gradient of that line tell us? And number six, what does the area underneath that line tell us? And finally, number seven, you have done integration before. That's asking you to integrate that function, 12x squared, with respect to x. So can you remember what the solution is, or what to do? So number one, who would like to tell me what the differential of that function is? Yeah. 12x squared. Yep. What notation are you going to use for the differential? Right, anybody? dy by dx, yeah. The differential, the notation dy by dx is 12x squared. Good. So 3 disappears, that's just a constant. Power down, multiply by the number in front, take 1 off the power, that rule that we've been using. What does that differential tell us about the original function? Rate of change. How is that function changing with respect to x? So x is often time. How is that function changing with respect to time? And if I plotted the graph, what would that tell us about the graph? So what's something else you could have said apart from rate of change? The gradient. So if I differentiate a function, and that's the whole point of differentiating it, tells us the rate of change of that original function, or the gradient of the line. And if we look at the graph, in other words, so the gradient of that line, I can find by differentiating the function. If I knew what that function was that related the velocity to the time, I could find the gradient of it by differentiating it. And if I found the gradient for a velocity time graph, what would that gradient tell us? What word best describes that? Any ideas? what's happening to the velocity as time goes by. So what do you think the gradient's telling us? Right, the acceleration. And looking at that straight line, what can I say about the gradient? It's uniform, right, so it's a constant or uniform acceleration. If it wasn't a straight line, it was a curve, this would still be telling me the acceleration, but the acceleration would be changing. Okay. What does the area underneath here tell us about the motion? Displacement, good. The displacement or the distance travelled. Well done. And to think about the displacement, what does this area tell us? Well, if I were to try to find this area, literally find this area, then I've got a particular shape, a trapezium, so I would split this maybe into two parts, turn it into a rectangle and a triangle, find those two areas to find out what it was. And the units would be the units of velocity multiplied by time. So the area would be velocity times time. So if I wanted to find the area and I wasn't sure it was telling me, I'd multiply the units for velocity, meters per second, by the units of time. So they cancel and we're left with meters. So it must be a displacement, a distance we're travelling. If I'm travelling at 30 miles an hour for 2 hours, I've gone 60 miles, that sort of thing. So with that in mind, we might be able to think about what 5 and 6 are in here. So it's the same idea. Again, if I knew the relationship between the force and the displacement, x, or the extension rather, then if I differentiated it would tell me this gradient, constant gradient. What does it tell us about this particular material if I found the gradient? Young's modulus, right, you've just done that in your assignments, haven't you? How did you find Young's modulus? Hopefully you found the gradient of that curve when it was straight. So number 5 tells us Young's modulus, a value for the stiffness of the material effectively. So the steeper the gradient, the stiffer the material. What about number 6 then? What units is it going to have? Whatever it is. The units of force multiplied by the units of distance. Anybody care to hazard a guess? Stress? No. Stress would be, that's a force, isn't it? The amount of stress I put on something, so that would be newtons. Maybe you've not seen this before. A very useful quantity. It tells us how much work's been done. You might remember the formula. Work is force times distance, and that's exactly what we're doing here. We're multiplying force by distance, measured in Newton meters, and a Newton meter is actually a joule. And so it tells us the energy that I've put in, or the work I've done to extend that material, how much energy has been expended. The area underneath the curve, in theory, but in practice you always put in a bit more energy than you get out. So the work you do to extend it is the force times the distance, i.e. the area underneath the curve. So it's useful to be able to find the area under the curve. In a graph like that or a graph like that. We know how to find a gradient, we differentiate, and we'll find out that in fact we'll see that integration that we're going to be looking at today is a useful way of finding out what the area underneath the curve is. So if I want to find the gradient of a function, I differentiate it. If I want to find the area between 2 points, I integrate it.